In the heart of a barren desert, a silver ribbon stretching 2,712 kilometers suddenly appeared, slicing the wilderness in two. This is a never-before-seen engineering miracle, the world's first circular railway line running straight through the desert. To keep this silver ribbon from being buried by shifting sand, engineers lifted 496 kilometers of track high above the ground, using an elevated viaduct system. This design takes advantage of the 32-meter gaps between pillars to create natural wind corridors. When sandstorms sweep through, wind speed beneath the bridge increases by 20%, generating powerful airflow that blows sand across to the other side, instead of letting it pile up on the rails. This smart solution not only protects the structure long-term, but also cuts maintenance costs by up to 90% compared to laying tracks directly on the ground. In construction engineering, the greatest enemy is not hard rock, but instability. The sand in the Taklamakan behaves like a highly viscous liquid. This phenomenon is known as flowing sand. Under gusts reaching force levels 10 or 11, sand dunes can shift as much as 20 meters each year. If you place a conventional railway on this surface, after just one night of violent winds, the entire system can be buried under tons of sand, or worse, the ground beneath the tracks can be eroded away, leaving steel rails hanging, suspended in midair. Thermal hammer blows. The next challenge lies in extreme temperatures. Engineers call this effect thermal hammer blows. In summer, the surface temperature of the sand can soar above 70 degrees Celsius, hot enough to cause massive expansion in steel rails, leading to dangerous warping. In winter, temperatures plunge to minus 25 degrees Celsius, making the steel brittle and prone to cracking. This constant expansion and contraction creates a brutal materials science problem that very few countries are capable of solving. Building here is not simply about assembling concrete structures. It is a high-stakes chess match against the movement of the planet itself. Chinese engineers understood one thing clearly. They could not fight the desert with brute force. They had to tame it using the smartest laws of physics available. If you stand in the Taklamakan Desert on a sandstorm day, you quickly realize that every attempt to block sand with raw physical force is meaningless. Facing dunes that can move 20 meters a year and wind gusts strong enough to overturn heavy vehicles, Chinese engineers made a decision that would change railway history forever. They did not build tracks on the ground. They built a massive viaduct system to make way for the desert. Out of the total 829 kilometers of the Hotan-Ruochang section, the final link of the loop, as much as 496 kilometers, lie in the most severely wind and sand-blasted zone. To solve this, instead of traditional embankments, engineers erected 5 enormous elevated bridge complexes with a record-breaking combined length. Look at these numbers. The Ruochang Bridge, one of the longest on the route, stretches an astonishing 18.6 kilometers. The Yamulakute Lake Bridge runs for more than 13 kilometers. In total, over 50 million cubic meters of concrete and steel were used along the line. Why build such massive bridges in a place without a single drop of water? The secret lies in letting wind and sand pass through freely. Tests at Xi'an Jiaotong University showed that lifting the railway created natural wind corridors between the 32-meter spans. As air flows beneath the bridges, wind speed increases by roughly 15 to 20%, generating powerful currents that sweep sand away before it can settle. Thanks to this design, sand clearing maintenance costs dropped by up to 90% compared to ground-level tracks. The greatest challenge was not building the bridges, it was making the pillars stand firm. The sand in the Tarim Basin reaches an average depth of 300 to 400 meters. This is not solid ground. It is a moving body. Engineers carried out more than 10,000 geological drilling tests. Beneath the fine sand, they discovered layers of ancient gravel and sediment. To reach this stable foundation, Each of the more than 11,000 bridge pillars had to be driven 30 to 50 meters into the earth, about the height of a 15-story building. Rotary drilling technology was used with special diamond drill bits. But a problem appeared immediately. Loose sand collapsed the moment the drill was pulled out. The solution came in the form of chemistry ultra-dense bentonite slurry. This mineral clay mixture was continuously pumped into the boreholes, forming a sealing film and counterbalancing hydraulic pressure that held the walls firm like steel until reinforced concrete could be poured in. The desert does not contain only sand, it also holds salt and alkali, concrete's greatest enemies. Groundwater in the Taklamakan carries sulfate levels 10 times higher than normal. With standard concrete, bridge pillars would crumble in less than 10 years. Materials scientists developed a new generation of sulfate-resistant concrete, combined with polymer additives that sealed even microscopic pores. After casting, each pillar was wrapped in a special moisture-retaining membrane to block salt intrusion throughout the curing process. And then there was temperature. During construction, day-to-night swings reached 40 to 50 degrees Celsius. Sudden thermal expansion and contraction could crack massive concrete structures from the inside. The solution? Smart temperature sensors embedded deep inside each pillar transmitted real-time data to a control center. If core temperatures rose too high, an internal cold water piping system activated to cool from the heart, ensuring absolute structural stability for a service life of up to 100 years. Now imagine transporting concrete beams weighing over 150 tons and measuring 32 meters long across hundreds of kilometers of roadless desert. China deployed 96-wheel ultra-heavy transporters with independent hydraulic control systems, crawling slowly over sand dunes like mechanical beasts. Each beam was prefabricated at mobile field factories located 50 to 100 kilometers from the site to minimize deformation during transport. Installation was carried out by a self-launching girder machine, a 500-ton mechanical monster capable of moving from pillar to pillar and positioning beams with accuracy under 2 millimeters. This was no longer a construction site. It was a massive industrial production line operating in the middle of the desert. If the elevated viaduct system is the hard shield, then the biological defense network China built is the soft shield. A miracle combining biology, water engineering, and artificial intelligence. You are looking at 50 million square meters of straw grids and more than 13 million trees, transforming the color of an entire region. Engineers did not plant trees randomly. They designed a highly scientific 3-layer defense system. Outer layer, located 200 to 500 meters from the tracks, stands a 1.5 meter tall polymer fence system that reduces the initial storm wind energy by 30%. Middle layer A, massive buffer zone made of 1x1 meter straw grid cells. In total, 50 million square meters of straw were laid. Why straw? It increases ground friction, prevents sand from being lifted by wind, and most importantly, creates a microclimate for microorganisms to thrive, preparing the soil for the next stage. Inner layer A, narrow forest belt stretching 300 kilometers, surrounding sections of railway built close to ground level. Choosing the right plant species was a matter of survival. Botanists screened hundreds of candidates before selecting 3 elite champions. Desert apple tree. With roots reaching 20 meters deep, it serves as the strongest sand anchor. Red willow. A salt-eating tree capable of surviving extreme alkalinity and scorching winds. Haloxylon. A leafless species that avoids water loss while performing photosynthesis through its green branches. The statistics are staggering. More than 13 million trees were planted along the Hotan-Ruochang line. The miracle is their survival rate, over 85%, an almost unimaginable figure in the Taklamakan Desert. How was it achieved? To sustain 13 million trees, China built the largest irrigation system ever constructed in a desert. 114 deep wells were drilled, reaching depths of 100 to 200 meters to tap ancient glacial groundwater. A drip irrigation pipeline network with a total length exceeding 10,000 kilometers long, enough to stretch from Beijing to Paris. AI-controlled management. Not a single tree is watered by hand. Internet of Things moisture sensors are buried deep beside the roots. When soil moisture drops below 15%, the control center automatically opens electromagnetic valves, delivering precise droplets of water to each tree. This system saves up to 80% of water compared to traditional spraying, ensuring every precious drop becomes life. Now, back to the steel rails. In the desert, rail temperatures can swing from minus 30 degrees Celsius at night to 75 degrees Celsius at midday. Across hundreds of kilometers, thermal expansion pressure becomes enormous. Without proper control, the rails would bend like ribbons. The solution is continuous welded rail technology, hundreds of kilometers of track without a single traditional mechanical joint. Thermite welding process. At desert junction points, a mixture of aluminum powder and iron oxide is ignited at 2,500 degrees Celsius. The molten steel flows into molds, forming a seamless molecular bond. Thermal stress locking. Engineers must tighten rail fasteners at the neutral temperature, usually around 25 degrees Celsius. When temperatures rise to 70 degrees Celsius, the rails experience immense internal compressive force. But thanks to ultra-strong elastic clamps, each capable of holding up to 10 tons, the rails remain firmly locked in place, unable to shift even a single millimeter. Why not use gravel ballast? In the desert, gravel is a disaster. Sand infiltrates the gaps between stones, destroying drainage and elasticity. After just a few sandstorms, the ballast bed turns into a rigid sand-concrete mass that damages trains. To overcome this weakness, China adopted a precast concrete slab track system. These multi-ton concrete panels rest on a special elastic layer that absorbs impact forces. The entire system is laser-aligned with extreme precision, with errors limited to just 0.1 millimeter. The result is that despite blistering heat and blinding sandstorms outside, trains glide smoothly at speeds of 160 to 200 kilometers per hour, with passengers barely feeling any vibration. The modernization does not stop there. The entire railway is managed through digital twin technology. Beidou satellites track bridge pillars and nearby sand dune movement with millimeter-level accuracy. Autonomous drones. Every week, fleets equipped with infrared cameras and LiDAR fly the route to monitor plant health and detect abnormal sand accumulation. Seismic sensors placed along bridge spans provide early warnings of geological vibrations from the nearby Kunlun Mountains. This is no longer a silent structure, it is a living system, an intelligent network constantly adapting to survive in extreme nature. Every passing rail, every drop of water falling at the base of a red willow tree is the result of millions of calculation hours and the quiet dedication of more than 12,000 people. By now, one big question naturally arises. Why? Why spend more than $3.5 billion and mobilize tens of thousands of people just to build a railway looping around a barren desert? The answer lies in a strategic vision stretching across decades. Beneath the scorching sands of the Tarim Basin lies one of the continent's largest reserves of oil and natural gas. But even more important are the rare earth elements, often called the vitamins of modern technology, powering everything from smartphones to guided missiles. This railway is the key that unlocks that treasure, transporting strategic resources to eastern industrial centers in the most efficient and cost-effective way possible. From a logistics standpoint, this line serves far more than domestic needs. It is a critical link in the Belt and Road Initiative, By connecting oasis cities like Hotan and Ruoqiang to the national rail network, China has transformed Xinjiang from an isolated dead zone into a thriving trade gateway, directly linked to Central Asia and Europe. Imagine the lives of people in remote oasis communities. For centuries, traveling to the nearest major city could take days on camelback or in aging vehicles along dusty sand roads. Today, modern high-speed trains glide smoothly across the desert, delivering fresh food, medical supplies, and opening doors to education and tourism. This is not just infrastructure connectivity, it is a connection of hope and future for millions. We are witnessing a geopolitical and economic transformation, where cold steel rails are warming lands forgotten for thousands of years. From above, the railway circling the Taklamakan Desert looks like a massive silver ring protecting and reviving a harsh landscape. It proves that humanity no longer seeks to conquer nature through destruction, but through understanding and intelligent adaptation. This project sends a powerful message to the world: no land is impossible to develop, and no barrier is insurmountable when we possess enough determination and intellect. The elevated bridges, sand-blocking forests, and seamless steel rails will stand against time and storms like a living monument to a new era of human achievement. As the sun sets over the Kunlun Mountains, golden light reflects off silver train bodies gliding across the sea of sand, reminding us that future technology and wild nature do not have to clash. They can coexist in a new harmony, where humanity guides the flow of progress. We hope this journey into decoding this mega project has given you fresh perspectives on the power of modern engineering. In your opinion, is building superstructures in deserts a conquest of nature or an inevitable step in humanity's intelligent adaptation? And which country do you think will be the next to create similar wonders across the planet's harshest landscapes? Leave your thoughts in the comments below. If you enjoyed this content, don't forget to hit like, subscribe to the channel, and ring the notification bell so you can continue exploring the next frontiers of human ingenuity with us.